מאפיין אנשים ממש רציניים ביותר. אני לא חושב שזה דבר שכל כך ראוי לזה.
לא, בסדר.
מה גם שהורדתי את התוכנית ושיחקתי, הורדתי את התוכנה ושיחקתי איתה. זה גרשת. יש משהו ג'נטיק אלגוריתם, זה עושה אותי ספישי. טלי, אתה צריך לעזור פה עם ה...
הם לא צריכים תסתתר לי.
לא, אבל... אתה יכול לעזור טלי עם ההשמעה?
סאונד, און, אוף, חזק, חלש, כל אלה?
צריך להיות בסדר, בדיפולט.
עכשיו, מה, אנשים התחרשו שם?
לא, זה אחלה עבודה, הורדנו את זה אז.
לא, זה הגיוני שקצת. צריך להיות חזק טיפול.
לוקח משהו וחורש אותו.
בקטע של היסודיות.
חורש אותו וזה עושה שני מאמרים, כי הסדר בראשון הוא לא משוכנע שזה לא תמיד טוב, שזה קודם ואחר כך. אז הוא הפך את כל האקספרימנט לתוצאות.
טוב שיש אנשים שעובדים מסודר, מה?
פרש הוא פרש.
מה זה פרש? הוא לא...
אני רציתי להתחיל, אני אגיד איך סוג של חזרה על מה שטלי אמרה, נתנצל. אני עושה איזה משהו שהוא אפסילון מור, זה נחזור על משהו. אני אראה אחר כך סוד מה שאתה שומע אתה יכול בזה זה דיגיטל. מצאתי משהו ברוק. קורה שם בדיוק משהו שנפלה לי נושא נורא ארוך והוא היה קצת סוד. יש לי שיטת סטריאוטיפ מהשישה. כל הדברים לדעת שהוא יעלה
תכף אני אראה דאטה תכף אני אראה לך את מה שכל פאפה עשה והוא בדק 20 אותי. תכף אני מנסה להסביר למה. אני מקשיב לך, אני רק כאילו. זה בדיוק. כן, הוא מצטט. Field Duration Illusion. אבל מניש כתב על זה? מעניין. הוא כתב משהו, הוא כתב מודל? טוב, אז אתה רואה, זה לא מיצינו עוד את הפוטנציאל של ה... אני הולך להגיד על זה מה שברונו ידע, אבל אולי הוא לא ידע על העבודה של מניש. וגם אם הוא ידע, הוא לא בטוח הצליח להבין את זה. כן, אני תרגמתי את כל השקפים של נפתלי לאנגלית. זאת אומרת, כל מה שאני משתמש, אבל זה כי...
כל כך גדול שכמעט תקע לי את המצגת.
כן.
הוא עשה שם משהו
הוא הצליח לעשות את הדברים הכי... כאילו, יש לו שקף שבאמת צריך לתפוס 200K לכל היותר, ואחר כך זה נתקע לו והוא לא מבין למה. רק כן, טוב. Okay. So this is the last lesson, and we will start. We will finish as we started by four very short presentations, and I will start now. So actually, it's kind of a recapitulation of the. It's not on the. Take a while. Working? Okay. So it's kind of a recapitulation of things that mainly Tali Wagner mentioned last week. I think it was a magnificent lecture, and Ronnie pointed out during the week that there is a very nice paper by Bruno Repp that actually deals with the same subject. So I decided to do a variation, two variations on those themes. Okay, so the first variation is about sensory motor synchronization limits and the piece that we heard last week by Beethoven. So if you recall my lecture 2 weeks ago, I tried to discuss the properties of sensory motor synchronization, the system that enables us to entrain to rhythm. And one of the topics was a demonstration that the system is limited, that there are some cognitive and there are some limitation on the range of synchronization. And we mentioned this kind of magical numbers that this system operates in the range where the beat is between 200 and 2000 milliseconds. If you remember, we did several experiments in class where we tried to show that. Okay, so now Tali Wagner has suggested us to see if this cognitive constraints holds in the context of real music. Okay, so does real music obey the limits of sensory motor system? So I just want that we listen again to the piece that we heard last week. This is the opening notes of Opus 111, so, this 32nd sonata of Beethoven, second movement, played by Claudia Rauh. Okay, so this music is very slow. The beat is about 1800 milliseconds, and it's just on the limit of our cognitive ability. This is the limit of the motor system, of the sensory motor synchronization system. So was Beethoven too deaf that he didn't know the limits of the constraints of the system? And I recall you the experiment that we did in the class. We tried to tap to very slow music, in this case not very interesting, and we practically failed in class. And we mentioned several other evidence that shows that in this very slow range, the system collapsed. Okay, so Beethoven, was he too deaf in that time when he wrote this piece? So in the end of the piece, Beethoven is doing something also interesting. And this is again something that Tali mentioned. Tali mentioned last week, Tali Wagner mentioned last week that Beethoven in the end of the piece is using these very fast notes. It's a trill. Let's listen to it. So this is the very end of the piece. And then the main theme of the piece. Okay? So you hear this very fast tones up there. This is called trill. Alternation of two figures. Very fast. And it lasts very long, about a minute, more than a minute. The beat duration is very slow, but on top of this very slow beat, there are these very high, very fast beats. Okay, so it lasts 72 seconds in this particular performance of different pianists. By the way, this is Schnabel, a very famous pianist. And if you remember, we mentioned another guy that is holding a trill, and he was doing that again for about a minute. And this is Tom Grosset, the champion of tapping, of drum tapping. And just let's compare the two. So this is Tom Grosset at Las Vegas, and this is Schnabel, somewhere in Germany. And they are doing this movement in the same speed. About the inter-onset interval is about 52 milliseconds, okay, here and here. And they hold their trill in about the same time, about a minute, okay? So you see, Schnabel could be probably getting the world champion in drumming if he was trying to win this contest. And they're both on the limit of our motor capabilities, okay? And if you remember my lecture 2 weeks ago, you recall that this is not only a motor limitation, but it also echoes some perceptual limitation, and I think that maybe Eli will say a few words about it further on today. Yeah, I mean, it's a little easier with two fingers, but it is almost the same range. Yes, but I'm saying that it's almost the same range. There are some differences, but you see these very, very similar numbers. 2 hands and 2 fingers, very similar numbers. Okay, but the main point is that this is on the border of our capabilities. So were Beethoven trying intentionally to challenge our sensory motor constraints? And I think the answer that we got from last week, and this is a wonderful citation that Naftali Wagner mentioned from Kundera, the answer, according to this view, is that yes, Beethoven was engaged in trying to investigate these limits, and he was trying to show or to try to show this zoom in into the variation. And the nice citation that Kundera mentioned Pascal in the idea that we as human race lives between this between the infinity of the cosmos and the infinity within the molecular and the subatomic space, and the variation is a process of zooming in metaphorically into the music. And this is why he used these two extreme cases of, he used the extreme rates of sensory motor synchronization because he wants to give us the whole range of the possibility of this abyss between these two possibilities. And this is why he started in this very, very slow, typical tempo, not so typical to Beethoven music, and he ends up with this very, very fast event. Okay, so this was the explanation. I finished now the first variation, which is kind of a recapitulation on what we said last week, and now I want to discuss another variation, and this is related to the musical term that is called listesso tempo. Okay, so listesso tempo is a musical instruction that Beethoven handwritten in his score, and he wanted the performer to maintain the tempo of the piece during the entire piece. And I'm citing here Arthur Schnabel that said similar things to Arau that we heard last week, but Schnabel is really a very big authority in the piano world. Maybe was the teacher of your teacher or something like that. Maybe. No. Okay. So Schnabel said the feeling of one central tempo for the entire work must be maintained, especially when a composer increases the motion from one variation to the next, as Beethoven does both in Appassionata Opus 57 and in Sonata C minor Opus 111. This is our piece. The point is lost if the speed changes at all. Okay? So the piece cannot be performed according to this very famous pianist. The point is lost if the space changes at all. Okay? So just to explain what do we mean by the speed, because the music is not necessarily a tapping stimulus. Okay, the tempo is the music is not simply a beat that does not change for the entire piece. The idea is that the piece has a beat structure, a bar structure, and the bar stays fixed. The tempo of this bar is supposed to be fixed, but the bar is further divided when the piece advances to more and more subdivisions, and these subdivisions are faster, even though the entire beat as a enfolding unit stays in the same tempo. Okay, so I wouldn't go to all the details, but just give you a few examples. So this is the beginning of the piece, the theme. This is one bar. Okay, this is one bar. And then the same bar, when it comes in the first variation, sounds something like that. So this is the first same beat. Team, pam, pim, pam, pim. Okay, so this beat is further subdivided, and in the second variation, it's divided. In this case, it's divided to 9. Every bar is divided in the beginning to 3, then to 9, now to 12. Okay, but it's the same, supposedly same slow beat, and now to 24 in the third variation. Okay, so just to recall what we discussed last time, now I'm following a diagram that's called Ski Hill by Richard Cohn, and this diagram shows how the big unit here, this is one bar, is divided into 2 and 3, and we can see that in the arietta the bar is divided into 3, and then in the first variation it's divided to 3 and then further on to 3, but in the second variation it's divided to 3 and then to 2 and then again to 3, and in the last variation it's divided to 3 to 2 and then again to 2 and then 3. What we can see from this diagram, just simply show you if what are the divisions in the units. What we can see is that every variation further goes deeper into subdividing the bar into units and subunits and microunits. Okay, and there are alternation, different passes during the piece between division to 2 and division to 3. Okay? Do you remember that? Okay. So now we go back to the question of tempo, and the question is how fast is 1 bar? And I recall you that Schnabel and Claudio Arau said that the beat should be maintained. However, this is a number that Naftali Wagner showed us, and it seems that at least Arau wasn't doing what exactly he was supposed to. He didn't do what he said he was doing, and he was actually accelerating in the second and the third variation quite significantly. Okay, so last time maybe we can ask ourselves, maybe this is simply a question of this particular performer. Maybe Arau was not a good pianist enough, and maybe some other pianists were better, and they were somehow performing differently. So fortunately, we have a guy like Bruno Rapp, and he meticulously investigated 20 recordings of all the very, very famous pianists from, you have all the names you need on this table, and some of these recordings are very, very rare. He recorded them himself from the radio in Germany, in Austria, and he had this tape recording, and he analyzed this particular recording, so they are probably recordings that, very rare recordings that he had in his private collection. And surprise, surprise, it's not Arau only, it's all the pianists. They are all accelerating on the first variation, almost all of them, and most of them quite significantly. Okay, so this graph shows you the tempo of the first variation against the tempo of the second variation. You don't need statistics to see that the first variation is simply faster. Okay, so Listesso tempo, this is the instruction handwritten by Beethoven, maintain the tempo. So all the pianists, they don't know how to perform music written by the famous master Beethoven, Ludwig van. Okay. So, yes, and then the answers are very simple. So, Bruno Rapp went to the lab, and he asked people to tap along divided and subdivided beats to see if the phenomena is some echoes some kind of cognitive constraint on the sensory motor synchronization system. So he instructed people to tap either to a subdivided beat. Okay, so this is in this particular case, in the first experiment there was a simple beat. Okay, and then he asked them to tap to subdivided beats, something like that. Okay, the same tempo but subdivided, and then further subdivided it to 3, and see if people actually tap when they tap to this beat, if they tap slower. So the paradigm he used is what's called in the tapping literature continuation paradigm. It means that they have the stimulus, they tap along the stimulus, and then the stimulus stops, and they continue tap. And see if they tapped in the original speed or a slower speed. And here are the results. You should see this is the difference between the original ITI and the tap interval and the tempo. So you see before the perturbation, removing the stimulus, it was about 0. Okay. And then after removing the stimulus, there was one bit where people are quite confused because they stop having this guidance. But then after a while, they actually go back to almost the same speed as they were before. Okay? And this is about 0. You see this? So they coming back to the same tempo as they were before. But in the case of subdivision, okay, they actually tap much slower significantly. Okay, it's about 30, 40 milliseconds, 3 to 5% slower. Okay, so when they tap to subdivided beat, it's slow. Okay, so I wouldn't play the game, but you probably say, maybe this is a question of tapping is a little hard, and when you have this complicated stimulus, you get confused. Maybe it's only a question of motor behavior. Maybe it's only a motor constraint. So Papa Bruno did a perceptual experiment where he asked people to tap to a condition where in one hand they had two beats that they had to compare, two alternative force choice. If the first condition was not two alternative, but if it's faster, slower, or the same, and they compared between simple bits and simple bits, or sometimes simple bits and composite bits, okay, subdivided bits, and there was a consistent tendency to perceive subdivided bits as slower, okay. This graph shows that, this shift shows that, and then he also compared it in a different way, and it's significant.
What kind of musicians did he?
Oh, so he has in his first experiment, he had only musicians, but then he had a control group of non-musicians.
What kind of?
And the musicians are very well trained musicians. They are these master tappers that they come to the lab every week and they do all kinds of experiments. Each of them has more than 10 years, and some of them were pianists. Okay, so there were different instruments. There was one harpist, one clarinet, actually that behaved slightly different, and then of course he also controlled the order. So there's a question: maybe we only accelerate when we move between slow beats to divided beats. Maybe if we do it the other way around, it wouldn't work. And he did that also in a follow-up experiment. And it turned out that always when there is a subdivided beat, there is a tendency to slow down. Okay? And to conclude, he composed himself a very sophisticated variation that sounds something like. You got the point. So people performed this very sophisticated music, and they were pianists in this case that creates notes, and they were instructed really not to change the tempo as far as they could, and there was a small tendency of about 5 to 7% to slow down the tempo. Okay? So after all this work, it seems a solved issue. What?
Reduce the duration, not to slow down the tempo,
To accelerate the tempo. They reduce the beat. Can you reduce the? Can. Yes, there is this, but this was not significant, and it was all a blame to be this clarinet player. So everything that went wrong in this article, when he excluded this particular clarinet player, then it's okay. And but this is as also Eli mentioned, this actually has a background in the literature, and people reported it in psychology. And it's called field duration illusion. We have a lot of evidence, apart from these particular researchers, that this happens also in other contexts. Okay, so we know now the explanation. Okay, I'm getting to the end. So, and we know now the explanation. So what is the explanation? Why Schnabel did not do what he was supposed to do? Because of this illusion. This illusion caused him to perceive something as equal tempo, where in reality it's a little slow. Okay? Yes, he accelerates.
But in the last figure, you showed that the pianist.
No. If I don't have time to that. I will get into it in the end. They did what they're supposed to. No, they did what they're supposed to do. I'll explain it afterwards. Okay. So we have an explanation, and this is it. This is the effect that caused this thing to happen. But if you take the numbers and see the numbers, you see that this explanation hardly explains any of the acceleration of any of the pianists. Okay, so this is a table that shows the percentage of this effect is about 5 to 7. It's this effect of about 5 to 7%. Okay, and we see how many of the pianists accelerate in this rate. And we see that almost all the pianists accelerate much more than they were supposed to do if they follow this particular effect. Okay? And especially of interest is this Schnabel that reported himself to not to change the tempo at all, and he was doing the largest deviation, about 34%. Okay? This is much more than any of the effects that any of the musicians showed in the lab.
The red accelerated and the green one slowed down?
No, the green one are the ones that you can explain by this effect. It's about 5%. The white one are the ones that didn't accelerate significantly.
But they were all went to the same.
All but these particular two accelerated.
בווריאציה השנייה קורה שם משהו מאוד מעניין. ויותר לאט מהביט הוא יותר איטי. למרות שקצב הריתם הולך להיות יותר מהיר.
No, but it's just a change of notation. 6/8 is equal 9/8. So that's the way that most of the pianists perform it. So it's a matter of notation. It's a matter of notation. The beat didn't change. It's just you write 6/8 instead of 9/8. No, what? No. In second, the difference. Yeah, I'm not getting into the difference between the second and the third. Actually, the paper is dealing with that too, and there are differences between subdivision to 2 and 3. And this effect also happens in the lab. Okay. So, but this is not the main issue, and I have to finish now. So, what I'm going to say, just to conclude, is that just to conclude the story. So, the story is like that. The explanation that some of the psychologists have in order to explain this effect, why we accelerate when we have more events, is that cognitive load causes us to process fast events slower, and therefore, in order to equate our feeling, this is explanation of, we actually accelerate, okay? Because we think it's slower. We perceive this as slower, although it's not slow, and that's why we accelerate. And this is why somehow it's sometimes confusing, but it's always consistent with this explanation. Okay, I'm ready to listen. But this is and what we did see that this was not enough to explain what pianists did, and actually what they did, they exaggerate much more this tendency. Okay, and this is consistent with a lot of experiments they did in studying of performance, where you see that musician tends to do much more than they are supposed to do by the tendencies that are inflected upon them from the system itself. And this is very interesting thing, because the consequence is that actually when we study very nuanced and very small effect that affects performance, we might understand something about the origin and seeds of how pianists and how musicians are actually doing what they are doing when they actually perform music. So this very small effect, no, it's just 5%, it's not a lot, actually caused, if you believe the stories that I just told, caused this exaggeration process that turns to be important aspects of expressive timing. This is it. Okay, I have to tell. I can answer the questions, but I'll do it when we change roles here, because if not, we won't have a break. So I'm ready to take questions if you. Yes.
I don't really see the point in looking at pianists. I mean, do they have studies with drummers also?
Yeah, so this particular issue was studied also in drummers, and
The same effect.
the same effect. Most of these studies in this field of sensory motor synchronization were done in a very small group of musicians, and there's always a question whether musicians and non-musicians show the same behavior, and there's some differences. But the results, apart from some small surprises, shows that the results are, roughly speaking, very consistent, and the effects are robust to this manipulation. I don't know. I'm not sure. I'm not sure that it was studied in this.
Rep's paper, the quote from Karajan,
Yes.
saying that he didn't do it.
Yeah, I mean, yes, but the rep was very suspicious about what exactly the experiment, because he was citing Karajan, that Karajan was undergoing some experiment where he was supposed to maintain tempo, and Karajan said he was very successful in doing that. But then Rep looked to the people that actually interviewed Karajan and looked through the experimental data and asked them whether they actually did this experiment, and he discovered they didn't do this experiment at all, or at least was suspicious about the fact that the experiment had occurred. So I'm not sure that this would be an example. But I think that it's an interesting question.
מרי, לפי מה שאמרת, זה לא אמור מווריאציה לווריאציה ללכת יותר מהר?
Yes, exactly.
וזה לא קרה? לפי נתונים של הרע, או לפחות...
No. The beat duration is faster, is shorter. The numbers are smaller. No. The question, no. This is important issue. This important issue. What you are asking is if further subdivisions create further effect. If it's kind of a linear effect. The more you have subdivisions, then it's supposed to be faster. The answer is also in the experiment that Rep did in the lab, it wasn't the case. Not necessarily if you divide more the bit, you get more and more effect. And the effect is certainly non-linear. Okay, there is some kind of effect, and it's saturate, and sometimes there even the reverse effect. So it's not always like that. So in a way, this is consistent with the experiment in the lab. Okay. Okay. I think we have another minute. I just want to emphasize that it's a kind of a speculative approach to tell this story, and I was in purpose kind of trying to show that. But if you believe this particular story, I think it's very interesting to see how there is some constraints on the system that are in a way translated to an expressive part of the expressive element of performing music, and this I think the point of where I think it's an interesting story. Okay.
Okay. Hopefully I'm set now. Sorry for the time. So we sort of decided to follow up on Naftali Wagner's talk last time, and all of us decided to look again at the Opus 111 piano sonata. So I'm also going to do a little bit of recap, going back to my notes in my lectures and trying to see again how they apply to this piece, or at least some examples within this piece, and also show you a little bit of empirical data related to Beethoven sonatas and the topics that we were discussing. So if you recall, I suggested in my first talk that music is a safe playground for the brain to exercise in a condensed form what it usually does and gets rewarded for. This is identify patterns and auditory objects. And in music, we could study this process without the mediation and interference of language. And I still maintain that one of the reasons why music is so attractive for studying perceptual processes and brain is exactly this reason. It is very structured on the one hand, and yet we don't have verbal tags to name things. So we use the perceptual process all the time. And funnily enough, I suggest we didn't really integrate our thoughts before, but I think that in art in general and in music, and one example was shown just before by Nori's lecture, is that artists push these limits as far as possible and even beyond. And this is one idea I wanted to show today too. I also said in one of my previous talks was that one of the nice things about music is that it creates a world of its own, a world of objects, of musical objects. And in each listening to the piece, we sort of have to follow up and understand what these objects are, to compare them and see how they change along the piece. And it is the responsibility of the composer to define, to help us understand what are these objects within the stream, the auditory stream, and sort of draw our attention to what is important within the stream, because there is a lot of information going on in there. And I also try to show that cognitive reference points, the way music is organized using regular beats, using scales, using harmony, all of these assist us to code and remember these objects and be able to compare them as the piece progresses. And so some of these points I want to show in the piece we are looking at. So here's just the top voice, and the bass of the arietta is the theme of the Beethoven piece that we sort of are all familiar with by now. And I want to point out to a few elements here. The first one is, of course, the first notes that you hear. Sorry. Nori, can you help me? Okay, so this is the first motive that you hear. And you can see that the rhythm and the melody repeat many times even within this arietta. And they will serve as a central element across the variations, especially in the first variation. You can see that it is composed of a long and a short note, and a repeating tone, which is, in this case, G, and we will see that the repeat of the tone is important, and also the pitch of G is going to be very, very important. And you can see that the repeat of the tone sort of looks back, is related to the previous tone, but also leads to the next tone. And so we will have many of these double repetitions of tones across the piece. Another feature to note is this special part here. Funnily, as Nori showed in terms of rhythm, I can suggest that in terms of pitch, one of the things that Beethoven looked for was very low notes. In the piano that he ordered from Broadway, from England, he wanted an extension of the piano, that it would include more pitches, and especially towards the lower register. And he uses this very effectively, and it's it's sort of stressed because of this terrible MIDI sound, but you can hear it here. Should hear it. Where can I raise the sound? hear it again. Okay. Hopefully this is not too much. I think this is it. Okay. So I took the very slow tempo of 33. Of course, this is very bare. It doesn't include all the notes. Here you can hear the very low bass notes. It's much less accentuated in the real playing because of the octave doublings. Of course, you have this very stressed minor part in A minor. Mainly because it's very bare. It's only the top voice and the bottom voice. So one more thing I want to note here. So we have this motif, the repeating G tone. We have this part that is stress. In the soprano, we have the rising chord. Da, 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 da. And this part that is stressed by the very low bass going down there and one passing chromatic note here is going to be a very important point or a very important sort of cognitive reference point because it's going to be very clear in the next variations. Even when Beethoven shifts and goes to very different tones and variates very exaggerately, this part is always very clear. You will always be able to find yourself within the variations once you hear these rising tones and this motif. And the minorization, these are the four features that you can see here. In the next slide, what I wanted to show you was, again, how one could play with the expectations that Beethoven, of course, avoids not being too ridiculous. But if we just repeat the first da 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 da, so we have the E, which Beethoven evidently gives us, but he would never give it like that, but he would delay it a little bit and then present the E as it should be. The same way we see here, da 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 da. That's where we would think this would go. He never gives the A. He sort of delays it, even not in the soprano, not even in the part where when he goes to A minor. And of course, he goes upwards and then downwards. So all of these very minute details are what make this theme, of course, majestic and not ridiculous like in my example. I also suggested that we engage a lot of the time in identifying the patterns and comparing them. And I suggested that it's sort of like a game when you have a figure that's within a background and you have to find the figure, you have some sort of an aha effect once you do find it, some sort of enjoyment when you can detect the thing within the variation, and probably the theme and variation is an excellent sort of musical form to practice this thing. And we also have clear prediction not only about what is going to happen, but also when. I'm going to play the second variation. You have the first variation in your mind already, and I want you to really try to rate how similar you think it is to the theme. You know it's a variation. I told you there will be some very clear features in them, in both of them, and yet try to, we're not connected. Let me play it from another place. Funnily enough, I also have Schnabel's performance. I should have it somewhere here. Wave, wave, wave.
I think it's this one. 10 piano sonata number 2.
Yeah, that's good. Okay, he's very close to around tempo, so I'm not going to present. I want to go to the second variation, somewhere 255, something of that sort. Okay, it's the end of the theme. Moving back from the minor to the major. Here. How would you rate it on a scale from 1 to 10? 1 is definitely different. 10 is really, really similar. Where would you rate it? Pretty similar. Like what? 6, 7, 8, 9? 7, 6. Okay. Not 9 and 10. Okay. Something. At least not when you first hear it. Okay. Without knowing the piece. Okay. Of course, it has all these motives. Da, 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 da. So this is exactly the same motive that we heard in the theme. We have the G repeating all the time. You can see it in the notes in the full arietta here, and it repeats as a very prominent note here. We have a lot of chromaticism, or many notes that lead. So you see these sharp notes leading to the next note, C sharp going to D, and D sharp going to E, and F sharp going to F, which is in a miniature was sort of suggested here in a very cliche way, but I think it's related. And yet it's different in character, in texture, in rhythmic motion, in extent and of use and of chromaticism and so on. So the general feeling, the general gist is it's not that related. Yet when you overlay just the top lines, this is what you get. The top is the variation. This is the theme. are there. They are just not in the right place. They often sort of are either delayed or too early, come in too early. And what we have is insertion of notes between the notes that we are expecting, sort of a phenomena that Dowling called interleaved melodies. I'm going to present to you another example, something from the lab, and I think you will understand the relationship in a minute.
Demonstration 5. Segregation of a melody from interfering tones. A familiar melody is alternated with distracting tones that are drawn randomly from the same pitch range. On each presentation, the melody is transposed upward in pitch. Note the point at which you can identify the melody.
If there's any melody, don't shout it out. The one who first hears it, be quiet. Someone has it? Raise hands, don't say. Okay. Got it? Someone has it? Not yet. You have it. All of, okay. Think it's once more? No. Okay. So, you have it. Okay? You know what was the melody? Come on. Yeah. Now, when you have it in mind, listen again. Just a few seconds.
Demonstration 5.
Okay.
Segregation of a melody from interfering tones. A familiar melody is alternated with distracting tones that are drawn randomly from the same pitch range. On each presentation, the melody is transposed upward in pitch. Note the point at which you can identify the melody.
Okay. So once you know what to look for, it's going to be much easier. But it takes a while to. So it's like in the variation. No, you were presented with the melody. You should know what to look for, but you have to take the effort and make it. Okay, I'm going to wrap up with two examples. One is from the middle of the piece, and I too sort of was fascinated by the trill. If you remember, I talked about the trill also in the other Beethoven sonata, and it's interesting to think how he uses this sort of very technical phenomena, like just alternating two pitches in a variety of ways. And I wanted to stress just one point here, not only the trill and the A tone that sort of was abolished from the first arietta. It's here in the minor, it's A flat, but also look at this point here and listen to it. When we get to these three notes that sort of identify exactly where you are in the arietta, and it's against very low bass notes as presented in the arietta, but here it's really in a very bare form, like I presented in my MIDI example, not with the whole chords as it is really in the arietta. not sure I'm going to present the whole thing because we really don't have time, but I want to point to a paper by Stefan Kirsch and Zamler from 2008, where what they did was to take Beethoven sonatas and present three alternatives. One is what the composer did, which is usually something that's original, unexpected to some degree, versus correction of the composer or being, making a very regular sort of chords, or a very unexpected chord, like some of the examples that we showed in the chorales or in the chord progression, but this is in real music. And let me just play these examples. Okay, so whoever knows the piece, this should be very surprising. And this is the original. This is Beethoven, not the other way, previous one. And of course you can ridiculize this and make it really And the nice part of this study was that they compared MIDI renditions to sort of expressive performances. This is the last example. I'm not going to go into the results. Okay, this is a computer playing exactly as the timing should be. And they examined galvanic skin response, looking for effects that are related to the expressive and the unexpected effects on the limbic system or on our responses to these effects. And you can see there are some significant effects. And they were also looking at brain responses, pointing again to these two components that we mentioned in our previous talks, the early component and the later one, distinguishing between the very expected one, which was not surprising for these participants who were non-musicians, and the unexpected or the original and the very expected ones. So we are pushing our limits also in terms of studying these, not only in very simple chord sequences, but going into real music as well. Okay, that's it. We'll take a break now. אל תדברי מיד מדי מהטלפון, זה עדיין יהיה מסובך, לא תרצי להיכנס
פשוט נראה לי ששומעים ספציפית שאני לא מכירה, לפי מה שראיתי
ראית אבל איזה פלטפורמה נגישה כזאת, שעכשיו בכלל... קוד של מטלב או משהו כזה?
לא ראיתי קודים, אבל בסדר, פשוט אני יכולה הם לא רק הסבירו אותם, הם לא ממש פירטו אותם, אני יכולה אולי למצוא את זה, אבל אני יכולה לעשות מישהו
אפשר לא לוותר על זה.
לא, כי גם יש קטע שכאילו זה לא רק ההסתברות של צד אחד יהיה הצד אחר, אלא ההסתברות של מרווחים, כי זה לא משנה איך זה, וגם ההסתברות של מה היה לפני זה, כי בהינתן מה שהיה לפני בכל צד, כי בהינתן מה שהיה לפני כאילו מלא כזה, אבל אפשר לעשות את זה, כי זה לא...
אני חושבת מהסטטיסטיקות שם, הדברים האלה.
אבל אני יכולה אבל להודיש לי שיש לי הזמן עוד אולי אני יכולה, פשוט עכשיו איך לי עצמי,
הזמן הפורמלי הוא
אז לא, זהו, חשבתי שאם לא זה, אז לא היה לי כבר אמרתי כאילו, אם אני מתעניינת בזה לגנטיקה במוח, לקחת שתי תיאוריות כאילו ולהגיד ביניהם. כאילו, אולי שאין כאן,
היום את ראית תובלה סופרת. אז דברים מנוגדים, כמובן יש את ההשפעה של הסביבה.
אבל כולם
מתכחש
בדיוק.
יש שאפשר לנסות לראות, להעמיד את הפרספקטיבה של יכולות אחרות, שמה שידוע על היבטים גנטיים של תופעות קוגניטיביות ומורכבות אחרות, כמו תופעות באופן כללי, אינטליגנציה, כאילו...
לעשות השוואה כזאת.
כן. שם אותם בפרספקטיבה.
אוקיי, אז זה נשמע, אני אקרא כבר במאמרים,
כן, אבל אני רוצה לנסות קצת יותר לחפש את המקום שלך. איפה הרקע שלך? בדיאלוגיה.
זה כזה גנטיקה.
כן. תראי, במקרה... דיברת על האבסולוטית,
כי לא דיברתי על זה, שהזכרתי אפשר...
נכון, אז אולי להנגיד את האבסולוטית ואת העמוסות בשני כתובות, כי את התמקדת בהרצאה שלך יותר על המוזיה.
כן, זה לא ממש מנוגד גם.
לא ממש. תראי, חושבים על האבסולוטית של יכולת יוצאת דופן ועל המוזיה כאיזה לקות יוצאת דופן.
זה משלימות, בדיוק.
אבל שניהם יחסית, נחשבות יחסית קונפיין, לא מופיעות על תחומים קטנים. תהליך העבודה היה מאוד דומה, תמיד בגנטיקה, לחלק להבין את ההתנהגות גנטית צפויה שם. תיכנס לאתר חינוך איך מפתחים. ובאו הם עובדים על יש לנו הרבה מאוד גימות לפני 5 שנים שהם מאוד קרובים לפתח מאז לא שמעתי מהם הרבה אבל קצת לראות מה יתקדם, אולי תקדם.
לא התקשרת אליי בסוף.
בואי עכשיו סקירה כזאת.
מתוך זה ביחד אפשר לחלק.
זה ממש יש לי
אני יודע מה תמיד אפשר
יש פה איזה משפט, יש כאן משהו, אני יודע מה זה, זה משהו, אני לא יודע איך לעשות לבחור את זה. אני יודע אבל יש לנו ישיבה פשוט מיד אחרי כן, אני רוצה לגמור את זה בפרופוזל עד מחר בבוקר. לא רואה איך אני עושה את זה.
נפגשים אחר כך, להביא את הדוגמאות, וגם את הממצאים, שלחת, נכון? יפה, תשמע,
רק שנייה.
לא ראיתי הרבה את ההחלקה, אתה אמרת שזה משהו עדין כזה, ניסיתי להסתכל איפה זה בא לידי ביטוי, לא סתם.
הפונים של ספגטי ואז רואים quality, לא, הוא בעצם מקבל שלם, זה כאילו דרך מין אידיאל, שאלה כמה רוצים
זהו, רגע, אתה באמת
למה
מתכוון
להסתכל.
יכול אינפוט כזה, אתה עושה.
לא, 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 לא. זה אותו דבר. 747 זה מהר, כל שהמספר יותר קטן, ככה זה יותר מהר, זה אינטוס וזהו. הייתי אמרתי איניטוס? אמרתי כל הזמן לא, אז כל הזמן גם פה אתה רואה את זה שהפוינט אוף המספרים הם למטה, כל ילדים יכול לעבוד
This class is very much like variations of a theme by Naftali Wagner, and actually after listening to the first two parts I feel like playing jazz, because essentially I just have to improvise over what my friends played before me, but and still try to connect it, of course, with the course and with the messages that we were trying to deliver here. So perhaps not surprisingly, we were going to relate to similar issues, although we haven't coordinated between us. So of course, I was also looking at these variations, these wonderful variations of Beethoven, and the first association that I had in mind of this very slow partitioning into three, and then another subdivision into three, and even before you go to the other variations, to me the whole thing reminded immediately what we call a fractal or self-similarity. And I don't know how many of you know what fractals are. Not all of you. But so essentially there is a mathematical notion that was actually discovered by artists in various ways and forms way before it was formulated mathematically. Only in the 20th century it actually was discovered by some mathematicians very early in the 20th century, in the beginning of the century, but was not entirely understood and recognized until computers were around. And it actually got to its most famous peak of interest and activity between the 50s and 80s of 20th century due to the rediscovery of the self-similarity in objects, in mathematical objects. And if you look at those three parts of the bar in Beethoven's, you can think about it as some sort of a triangle. And what he does next, or did next in the next tone, is essentially something like this, which is dividing this triangle into three different triangles, which are very similar to each other. And you can think about it. I didn't have time to actually prepare a real demonstration, and Nori was too busy with other things. But essentially, you can really play the notes as if you move along the edges of the triangle in the first
in the theme, and then when you move to the first variation, you essentially play notes on all these 9 edges of the split triangle and so on, and you still remember the big picture, but you have inserted somehow an internal partitioning. And of course, in principle, this type of transformation, dividing every triangle into three more triangles, could continue like this, and again, and again, and so on. And in principle, this is some sort of a very interesting mathematical transformation that generates objects, if I really continue it forever, that are known as fractals or known as self-similar, in the sense that every part of the object looks exactly like the object itself. And of course, every third of this object, if I just blow it up, and I'll do it in a second, recovers essentially the structure of the whole thing. And this type of mathematical geometry, self-similar geometry, became very famous and very important, actually, in both physics and some aspects of mathematics, as I said, about 50, 60 years ago. And it actually got its really peak of interest around the 80s, where due to mainly people like Mandelbrot and others who introduced the name fractals, and essentially this notion of this object, if you think about the dimensionality, the topological dimension of this thing, what do you think it is? So you would all think it's somewhere in the plane, so it must be at most 2, but actually it has no volume whatsoever, no area whatsoever. If I keep doing it ad infinitum, I actually take out all the area, and I'm left with something which has essentially no area, but has some sort of an infinite length. And actually, the dimension, in some sense, of this is actually fractional. It's actually log 3 over log 2, and this is why it got the name fractional dimension. But these are very interesting mathematical objects because of this new dimension of similarity. Now, essentially, what Beethoven started to do here is play the first iteration of this self-similar insertion, but in time, not in space. And actually, he almost continued. The second variation, again, doubles the frequency almost, was not exactly dividing it into 3, but actually dividing it into 4. So instead of taking those 3 triangles and cut them again into 3, he actually put some sort of a square here by cutting it into 2, and got the 12th bit and so on, and then 24, dividing it into 2 again. And it's actually amazingly interesting in view of our larger theory of surprise and expectations in cognition to try to understand what's actually happening here. Of course, he did it completely intuitively, or without, as far as I know at least, without using any formal mathematical understanding. But it turns out that this idea of self-similar objects really appear in art even before Beethoven. Actually, during the 18th century, some artists were playing with the notion of inserting an image within an image and so on, ad infinitum, and all this notion of infinite iterations of something looks extremely rich, but at the same time very boring. I mean, if I just show you the whole thing together, after exactly one iteration, you already understand the idea. I mean, essentially, the whole thing is just self-similar in the following sense: it can run forever. I mean, I can zoom in this Sierpinski gasket, as it's called, and after exactly 2 iterations, you understand the principle, and nothing interesting happens. So, in some sense, this is too self-similar, too obvious. But is self-similarity really part of what we consider rich and aesthetic? And this is actually a very interesting first part of my variation on this theme. And indeed, self-similar objects appear in nature everywhere. I mean, this is exactly why they became so famous. But they usually, in most cases, they don't appear exactly as self-similarity, but as an approximate self-similarity. So, for example, if you look at trees, so some trees, not all trees, but some trees, or some leaves even, have a almost self-similar structure. I mean, they branch into little branches that appear exactly in the same form and same shape. across several scales, of course not ad infinitum, but maybe 3, 4, 5 times. You can see this on leaves and trees. You can see this actually very clearly in objects which are more statistical in nature, like holes in cheese, in Swiss cheese, or like bubbles in boiling water, or like the craters on the moon, or whatever. There are many places where you see this statistical self-similarity, which means that when you zoom in, you really don't know where you are in terms of scale. It looks exactly the same, just like this zoom in on the fractal. You don't know if this was the big or the small or what side of the scale. It looks exactly the same again and again. Maybe it is surprising to some of you, but if you do this to boiling water, just at 100 degrees, if you look at the bubbles, and you just zoom in with the camera or with the telescope or the microscope, whatever you want, across maybe 10 orders of magnitude, or maybe more than that, you're going to see exactly the same picture. If I take the camera and magnify it, you will never know what was the scale of the image. It looks exactly the same. Why it looks exactly the same? Because there are essentially bubbles there on every length scale, and with no clear correlation length, as we call it. Actually, what physicists used to say about it, that the correlation lengths diverge. There's essentially no scale in the picture. Everything looks similar on all scales. And this actually, the fact that this appears in places in nature which we call these critical points, like boiling water. Actually, it happens in every phase transition in some sense, that some scale diverges. And this is actually almost the definition of a phase transition. And it's actually really the origin or the source of the mathematical understanding of phase transition, the fact that we can, as we call it, renormalize the image, go back to another scale and see the same thing again and again and again. So this is actually interesting mathematically, but the question that Beethoven is posing to us here, it's not only, okay, he was playing with self-similar embedding of some sort, but is it really beautiful? Or is there any aesthetic value to this notion of self-similarity? And I must say that there have been, again, during the 80s, mainly 80s and 90s, there have been several books on fractals and beauty, and fractal and aesthetics, and all sorts of examples and fractals in aesthetic, in plastic art, in paintings, and even a little bit in music. Actually, you can even download from the internet. I didn't do it, but there are at least 3 or 4 different sources of generators of fractal music, which can essentially translate some sort of self-similarity into notes and generate something which sounds the same on all scales in some sense. Obviously, there's something basically missing there. And as I said, I mean, so Beethoven is not really doing a self-similar transformation, just hint to it. But of course, surprised us at some sense by transforming it either by changing the beats or superimposing 3 on 4 and get this syncopatic notion of almost jazz and so on. But is it really a cognitive phenomenon? And this is something which I think we now may have the principle of trying to understand it. So again, if I move out of the fractals, you can actually, by the way, generate fractals like this with a stochastic process, with a random process, and essentially it's a very similar. You can actually program something like this yourself very easily. You just take 3 points and then randomly choose any one of the 2 points. Take a point at random and then choose one out of the 3 origins, the 3 corners of the triangle, and take half the distance to this point, and then do the same again and again, and you'll get exactly this shape. So this shape is also something which we call attractor. I mean, it's attracting some random process. Many things look like this, even if they start very differently. And what you see here is exactly this type of randomness. Essentially, it's done with an algorithm which has absolutely no idea about triangles or about this mechanism. You just take random directions and always half them. And you get this again and again. This is actually the reason why this is the basic mechanism why such fractals or such self-similar objects also appear in dynamics and in dynamical systems. And some of you may have heard about strange attractors and chaos, and they're all full of objects like this, which are self-similar because of this reason exactly. So some temporal process which always restricts time in some sense in an invariant way will automatically generate self-similar objects like this. Now, if you remember our talk, or at least my talks, and I think that Nori also mentioned it, we are trying to address everything through one principle, which is almost boring to me by now, but and the principle which I think is at least a good candidate for explaining different phenomena in cognition, is this idea that essentially our interaction with the environment is based optimally on one idea. I mean, on one concept, or one, as I call it, computational principle. Try to compress as much as you can the past of your environment, your experience, sensory environment, in order to make the most valuable predictions of the future. This sounds like a ridiculous principle for something like the brain, but I challenge every one of you to come with examples that I can't explain with this, in some sense. I mean, because it seems to be a very fundamental, a very wide universal principle of cognition. I didn't used to say it like this, but the more I look at it and the more examples we test like this, it seems like something, okay, try this first and then see what happens. And of course, the principle was extremely simpler. I mean, you try to make predictions, you compress the past, take as much past as you can, and of course, here again, the notion of time is critical. How much past, what is the time window into the past that you're trying to remember? And then try to make a prediction into the future, and what I claim the brain first order or zero order approximation is a good compressor of all the past history of our perception in order to make those valuable predictions into the future. Now, we gave you several, or at least one example where this principle can help understanding things. Actually, we gave more than one. The first one was actually this notion of reverse hierarchy, the fact that we first see the big picture and only later the smaller picture. We see things we perceive things in some sense in a top-down manner, which means that we actually make predictions and then test them, or we make hypotheses and test them. And I actually argue that at least large part of our perception, whether it's auditory or visual or whatever it is done that way. I mean, we first guess and then test, and then guess and test, and so on. And we do it on multiple scales, just like the fractals. I mean, we have in mind short and long scales of the phenomena. So we do it both in the immediate, very nearby millisecond time scale, but we keep in mind, or we try to expand this horizon, the perceptual horizon and the predictive horizon, the planning horizon, in both directions. And actually, we humans got very, very good at making plans which are way beyond the immediate future. I mean, almost every animal thinks about today. We give ourselves the credit that only humans think about tomorrow. It's of course not true, but we definitely think further away than any other animal around, and mainly because we managed to extend this predictive or planning horizon of our. So this cycle of perception and action really goes across many scales, from the sensory motor scales of milliseconds that Nori was talking about mainly, to scales of seconds, and then scales of tens of seconds and minutes, and then months and years and so on, days and months and weeks and years, and we actually think about tens and thousands and millions of years within our scope of planning and horizon, beyond our individual existence, of course. And this is quite remarkable. And the question is, what could give us this ability, this limited machine, our brain, to actually think in so many different scales, almost invariantly? And of course, the candidate for mechanism like this is actually we have a cognitive self-similarity in some sense. And maybe we are actually using the same routine that we use on short time scales, also on long time scales, and of course, this is, at this point, this is the only way to explain our ability to make recursions, to open parentheses in language, and actually think about different things in exactly the same way. The next hour, the next day, the next week, and so on. And the fact that we are able to make recursions is really one of the fundamental aspects of us as human beings, and of course of human language, and I claim also of good art. So this self-similarity, this really naive geometrical self-similarity of fractals, is really a very fundamental component of our cognition. And the question is, of course I can tell you a lot about it, but I'm not going to do it right now. So of course, besides explaining things like this reverse hierarchy things in auditory perception, the fact that we first guess the words and then perceive them auditory, that Ellie and I were talking about, and as I said, I mean, this is an immediate consequence. It's predicted by a self-similar predictive theory like this. I mean, we actually look at different scales and infer the smallest scale from the largest scale. And this is the only way we can actually perceive complex things, because otherwise our perception was extremely limited. If we had to do it bottom up, we know now this is simply impossible. We don't have the time, we don't have the computational abilities to do this. So this ability to move across different scales is really a fundamental aspect of our cognition and our behavior. You may not believe this, but the question I want to address now, okay, so we know more or less what we do computationally. We treat time and the environment around us, whether it's auditory or visual or whatever, as some sort of a stochastic process in time, something that moves in time, which is partially predictable. There are things which you can predict, and there are things that you can't predict. And what we do is, in some sense, generate representations across different scales here. Whether this past is 1 minute or 1 hour or 1 year depends, of course, on the problem. And in some sense, I argue that we are moving across these scales freely all the time because we are doing recursions. We're actually using the same predictive routine again and again. And if we're indeed using the same predictive routine again and again, then by construction, we don't have a choice but having a self-similar perception of the world. And this is actually quite nice because, first of all, what I want to focus about here, because this requires much more than a simple a few sentences from me. But as I said, the computational tool that we are building is giving us some sort of a quantitative curve that it's not only the curve, it's really what's behind the curve, the probability of predictions and the representation of the world, which are optimal in the sense that given this level of complexity, this is the best I can say about the future. And this curve is a property of the environment itself. But staying in different levels of this curve means that we are optimal with respect to some sort of complexity. But the more interesting the curve is, as I was trying to say, that interesting music is something which cannot be explained on one scale, but actually, once we understand it on the scale of seconds, we immediately look, or the music itself is challenging us to build another explanation on a higher scale, and so on and so forth. And the question is, in some sense, we can now ask, if it's good art, it should gracefully scale in some sense. And if it's very bad art, it can be explained by just one thing, and that's it. Okay, so this is something which we can test. And as I think I showed you, so Nori and I are working now on some sort of an extension of this principle that allow us to do it on essentially anything that moves, or anything. We can really calculate it for many, many different things. And here's an example. I'm not sure if I showed it or Nori showed it, but I like it anyway. So this is of course, a famous picture of Van Gogh. And what we do here is essentially try to calculate this information curve. How much information or how much more complexity there is in the picture when you increase your scale and your capacity of perception. And to some extent, you see that if you do it very poorly, using the wrong type of filters or the wrong type of kernels, as we call them here, you're going to essentially saturate and get all the information immediately and don't get anything else when you increase the complexity. This is some sort of a linear filter, never mind what it is. But if you do it correctly, let's say with something which really reminds of the true receptive fields of the neurons in our eye, or something like this, then you see that Van Gogh was playing it. It's a very naive game. We're trying to predict the color from the statistics of the environment in some sense here. But you can do it in a much more sophisticated way. And you see curves which really look like being interesting across multiple scales. So, as I think I said before, this can explain to me at least why we are attracted to good art. I mean, if I see, let's say, this picture from far away or for a very short time, and I see something very blurred and very, but even this very blurred picture, if I look at it through the right filters at a very low on this information curve, I already see something which may create some expectation, or which resonate with my understanding of the world. Maybe this is a person, maybe this is an animal, maybe this is a mountain, this is a building. This can be many things. And of course, this attracts me to the image because I'm immediately expecting something. And if the picture is nice, when I go up higher and higher on this curve, I'm going to see more and more details, which will pose more challenges to my perception, just like with good art. And eventually, so which will pull me to the pictures in a museum. I don't know if it happened to you. It happened to me many times. I see a picture 50 meters away, and I want to look at it because there's something in this picture that attracts me, And I argue that this something can be related to the curvature of this curve in some sense. I mean, how much you can really reveal about the image by getting closer and closer to it, by seeing it on multiple scales. And of course, in some sense, you can ask, okay, so what is the optimal perceptual curve that we can generate for real things, that really attractive things? Of course, one thing that comes to mind is a self-similar object. But of course, if they're truly self-similar, like those fractals, like this Sierpinski gasket that I mentioned, then of course you are not going to find it interesting, because after exactly 2 iterations you understand the principle and you go away. So you have to twist it somehow, and exactly the way that Batman is doing, and surprise in the rule itself, and keep generate interest. And this is precisely the secret of good art. By the way, the impressionists like Van Gogh surprised you again. When you get too close, things disappear in some sense. You see the brush moves, or you see things which are completely not what you expected, just black dots that are actually, from far away, they look like people. When you get there, you don't see people, it's nothing else. So actually, they pull you, and then they push you away to the right distance, where you really see things interesting and your imagination still works. And it's actually a clever trick, which was discovered only by impressionists. And I think something like this happens in music as well. There's something which is beyond what is really there, which is only in your imagination. And this is really very nice and directly related to generalization in learning and many other things. But notice that these curves, I really have no time to answer questions unless it's very important.
What about a picture of Jackson Pollock then?
The picture of what?
Jackson Pollock, for instance.
I'm not sure.
The guy who makes the sprinkles on the Jackson Pollock.
Yeah, Pollock. Yeah, of course. It's a good question. I think it's an art only within the context of regular art, which means that it's surprising you because it's so different. But once everything is like this, it's losing almost like most of modern art. If you take it out of the context of a museum, it loses its value completely. You know, you can take a toilet seat and put it in a museum, then it's suddenly an art because nobody expected it. But of course, this is a different story. I don't want to get into it. But of course, you can play this game because you already expecting things when you get to museums and you listen to music and so on, and you can break these expectations and twist it many, many times. Anyway, what I want to tell you also that this theory actually tells you that it doesn't really matter how these curves are generated. Just believe me, this is a purely mathematical phenomena. It's the appearance of some eigenvector of some matrix, which tells you that essentially in order to climb on the optimal curve, you really need to discover new fundamental laws about your environment. Something like, for example, this transformation that things can be self-similar is another dimension that will be discovered using mathematics like this. And without getting into it, if we are limited, we are not going to discover it. So this is, again, telling us something very fundamental about perception, about aesthetics. But if this curve is interesting, it should be, in some sense, self-similar. And indeed, for self-similar curves, we get something which looks like a power law, like things which are as surprising on every scale, so the curve should look similar to itself, and I'll come back to that in a second. I think that language is like this, and maybe also music is like this, but we'll come to this. Now, I just want, before I have to turn to Eli, who was going to throw me away, I want to say something about the perception of time out of this theory. So time is something elusive. I mean, of course, we have clocks, which give us regular time, but we already had today even that time is more subjective than it seems. And actually, if you take this theory seriously, then time has essentially two facets. One is the external time, the time that is involved with the changes in the external environment in the world. So this W is the outside world in some sense. And the other one is what I call the internal time, the intrinsic sense of time. And this, according to this theory, is related to the amount of information that we have about different concepts of time. So, for example, when we look further away, our perception of time further away into the past or into the future, we have less information about it. We forget things, we don't have enough details, and essentially our perception of time looks something like this. I'm sorry. So this is, I don't know if I showed you this picture, but this is something which I call the time fisheye. So we all know what fisheye lens is. I mean, so a fisheye lens has a high resolution, high magnification in the center, and very low resolution in the other side. So essentially, the further away from the center you look, the less details you can see and can capture. But something very similar happens to our perception of time as well. I mean, we actually further away back into the night here, if you want, I don't remember things very nicely. They compress in time. And the more I move into the further future, they also compress in time. So my perception of time in the present is a lot more detailed than the time tomorrow or the time 10 days from now and so on. This actually is, again, a fundamental aspect that allows us to plan efficiently. Because otherwise, if I had to think today, now, where is my foot going to be when I get into the car at the end of the day, I will go crazy. Of course, I don't know, and nobody should know. All I need to know is that I somehow need to get out of the building, and then my planning will take care of itself somehow, which means that there's some sort of self-similarity in our planning. Essentially, I pass it in very coarse-grained picture when I look into the future, and then when I get closer and closer, I somehow fill in the details automatically without thinking about it. Now, this is not only a nice mathematical view, it also explains how we can cope with a very complex environment. Now, just notice that it means that our perception of the tempo in Beethoven of the past notes and the future notes is very different from the perception of the tempo in the bar that I play now. Now, during the talk of Nori, I was trying to see if I can explain the phenomena of the slowing down or accelerating of the tempo. Of course, this is a complete joke at this point, but because I haven't thought about it enough. But it turns out that you can. Because if my perception of time, let's say, is logarithmic, or it's actually compressed in time when I look further away, and let's say that I'm actually trying to follow my memory of the rhythm in the previous bars, but I don't remember it exactly. I remember it through this fisheye lens in time. I actually remember it compressed. I actually remember it faster than what it really was. And that's why I accelerate. Of course, you can play this game the other way around, so I'm not sure it's an explanation, but this is very suggestive. Anyway, this notion of compressed time is really where our theory now develops and how it's related to learning and planning. But in order to know this, you should come to my next course next semester on perception in action. I think I stop here. Thank you. Moved too early.
Just want to say that it's a little clear that the lesson will be slightly longer.
No, I mean, this is improvised.
Try to have your patience about that, because that's the final lesson, and I think it's very important for all the speakers, for all of us to somehow conclude the discussion. And